All right, let's get right into it. Have you ever looked at the world around you and wondered about the hidden language of shapes and distances and angles? Well, today we're building your geometry toolkit from the ground up. We're going to start with the absolute basics, and by the end of this, you'll have a brand new way of seeing all the structures that surround us. So, you ready? Let's go.
So here's our game plan for today. First, we're going to unlock the power hidden in a simple line. Then, we'll figure out how to find its perfect center and use that skill to solve a fun little logic puzzle. After that, we're jumping from one dimension into two, getting a whole new angle on things, and mastering the protractor, the tool that lets us measure them. Let's get started.
First up, the number line. Now I know it looks almost too simple, right? But don't let that fool you. This right here, this is the foundation of measurement. It's the tool that takes abstract space and turns it into something we can actually define, measure, and understand with total precision.
Okay, check this out. We've got a line, and on it are a few points, each with its own little address, its coordinate. So C is at 2, A is at 4, R is at 7, and D is all the way over there at 10. Believe it or not, this simple layout is literally all we need to find the exact distance between any two of those points.
So, let's put this new tool to work. Looking at this line, how would you figure out the exact distance from point C all the way over to point D? Go on, take a second to think about it.
The method couldn't be simpler. Seriously, the distance is just the difference between their coordinates. You just take the bigger number, subtract the smaller number, and that's it. No crazy formulas, just simple, straightforward math.
And the answer is 8. D is at 10, C is at 2, so 10 minus 2 gives us 8. And just like that, you've got the first tool in your geometry toolkit. Awesome!
Okay, let's keep building on this. Now that we can actually measure the length of any piece of a line, what's the next logical step? Well, how about finding its exact center?
And we call this the midpoint. It's a really crucial concept, and it's not just some abstract math idea. This is the core principle behind balance in engineering, the center of gravity in physics. Heck, it's even used to create smooth, believable animation in video games. It's everywhere.
Let's try a quick one, right? Imagine you've got a line segment that starts at coordinate 3 and ends at coordinate 5. What number is sitting perfectly in the middle?
Finding the midpoint is basically just finding a simple average. You add the two endpoint coordinates together, and then you divide that total by 2. That's it. 2 simple steps that will get you the perfect center every single time.
So, for our little problem, 3 plus 5 is 8. Divide that by 2, and you get 4. The midpoint is right there at coordinate 4. See how these tools are already starting to connect? We went from distance to midpoints. So, what's next?
All right, it's time to flex those logic muscles a bit. We're about to tackle a problem where they don't give us all the numbers up front. Instead, they tell us that a bunch of points are all equally spaced, and we have to kind of play detective to figure out the rest.
Here's our puzzle. We've got a set of points on a line. T-O-U-G-H-E-R. Now, the most important clue is that the distance between any 2 points right next to each other is exactly the same. And our first piece of evidence, point T is at coordinate 15.
And now for our second clue. They're telling us that the coordinate for point U is 12. So, using just those 2 facts, can you figure out the distance of the segment from U to G? Let's think our way through this together.
All right, let's break this puzzle down. We know the distance from point T at 15 to point U at 12 is 3. Now we're told all the points are equally spaced. Between T and U, we have the points T, O, and U. Seeing that distance of 3 and those 3 points, the simplest solution here is that each space between them must be just 1 unit. It's the cleanest fit. So, if the interval is 1, then the distance of the segment UG is, you got it, 1.
And that is the magic moment, isn't it? The power of that one logical step. Once we figured out that the interval is 1, the entire puzzle just unlocks. The whole thing falls into place, and we can instantly find any distance we want on this line. It all becomes simple.
So far, we've basically been masters of a one-dimensional world, just the line. But the real world around us isn't a flat line, is it? It's got depth, it turns, it rotates. It's time we expand our toolkit and break into the second dimension. It is time to talk about angles.
So what exactly is an angle, anyway? Well, it's actually pretty simple. Imagine a ray is kind of like a beam of light from a flashlight. It's got a starting point, but then it goes on forever in one direction.
When two of these rays share the exact same starting point, we call that point the vertex. And that space between them, the amount of turn, that's the angle.
So we know we can measure the length of a line with a ruler, but how in the world do we measure the amount of turn in an angle? Well, for that, we need the final tool for our kit today, the protractor.
Let's take this angle right here. We'll call it angle ABP. And let's put our new tool to the test. Just watch how we line it up. Because with a protractor, getting it in the right spot is everything.
Here's how it works. It's just a simple three-step process. First, you take that little hole in the center of the protractor and place it directly on the angle's vertex, which is point B. Second, you line up the 0-degree line of the protractor so it's perfectly on top of one of the rays, in this case, ray BA. And finally, you just follow the other ray, BP, up to the scale and read the number it points to. And there it is. Ray BP clearly crosses the scale right at 150. That means the measure of angle ABP is 150 degrees. And boom, we've just successfully used our brand new tool to measure rotation. Simple as that.
You know, let's just pause for a second and appreciate what we've done here. We started with just a plain, humble line. And from that one single idea, we learned how to measure distance, how to find a perfect midpoint, how to use logic to solve puzzles, and then we took a huge leap into 2 dimensions to measure angles. You've just built an incredible foundational toolkit.
So think about it. We now have tools in our belt for length and for rotation. But what comes next? What other fundamental tools do you think we need to start describing all the complex shapes and objects that make up our world? That's something to chew on. Thanks for joining me on this one.